In the previous module, we have seen that the complex exponentials act as eigenfunctions of LTI systems. Meaning, if we give a complex exponential as an input, say a e to the power j omega t to an LTI system, I would get the same complex exponential with a change in the scaling factor. That change in the scaling factor we have denoted as h of omega, and the rest of the signal remains the same. And this scaling factor we have named that as eigenvalue of the LTI system. So the point that we have emphasized was that the input complex exponential, you are going to get the same complex exponential as that of the output with a scaling factor of h of omega. And we have precisely defined this h of omega. That h of omega we have defined as equals to integration from minus infinite to infinite h of t e to the power minus j omega t dt. And what is this small h of t? This is the impulse response of this LTI system. Now, in order to obtain more insights into this concept of complex exponentials, let's take an example. Let's consider an LTI system, something like this. Say y of t equals to x of t minus 5. Let's consider this system. Now this system simply delays the input signal by 5 units. Very simple linear time invariant system. Now let's try to give a complex exponential as an input to the system. So let's say if we have the input signal as x of t equals to say e to the power j 2t. Let this be a complex exponential that is being fed as an input to this LTI system. Now by mere observation we can see that if this is the input, the output is simply a delayed version of the input. Therefore the resultant output is going to be equals to y of t, that is going to be equals to e to the power j 2 times t minus 5, and that is equivalent to equals to e to the power j 10 times e to the power j 2t. Now you can see that here the output is the same as that of the input. You can see that from here the output is the same as that of the input, except with a scaling factor. We have already seen that scaling factor, that is the eigenvalue of the LTI system. Now for this signal being very simple, we can readily obtain very easily the output of this LTI system. Now let's prove this factor that we have obtained, the scaling factor that we have obtained. Let us prove that factor as eigenvalue formally using the expression that we have already obtained. So if we evaluate that h of omega using this equation, we should get the same value as we have obtained it here. So let us derive this h of omega formally for this example. But in order to evaluate that, we'll require h of t, that is the impulse response of the system. Now we know what is the impulse response of a system. in order to obtain an impulse response, we should give an impulse signal as an input to the system. So x of t, we must give del of t and observe what is the output. That output is going to give us the impulse response. So here the impulse response h of t is going to be del of t minus 5. Simple. If we give input as the impulse signal, the output is going to be a simply delayed version of that impulse signal, and that is the impulse response of this system. Now if you know h of t, we can easily calculate this h of omega. So what is h of omega? Now h of omega is going to be equals to minus infinite to infinite integral h of t, that is del of t minus 5 e to the power minus j omega t dt. And we know from the properties of impulse signal that if any signal is getting multiplied with an impulse signal, the output is going to be an impulse signal that is being scaled by a value of the signal being multiplied, and the value that is being scaled is evaluated at the location of the impulse. Meaning, if we simply multiply any signal, so e to the power j omega t is a signal, if you are multiplying that with an impulse signal that is being located at some location, the resultant signal is going to be the same impulse, but it is being scaled by the value of this signal e to the power j omega t at this location. So this is going to be equals to, now that is the shifting property of the impulse, that is going to be equals to del of t minus 5, that is the same impulse signal, but it is being scaled by the signal being evaluated at that location. So it is going to be j omega 5 dt. Now this being a constant, we can take outside the integral, and that is going to be equals to e to the power minus j omega 5, and the rest of the integral is integration over an impulse signal, that is 1. So the resultant h of omega is going to be e to the power simply j omega 5. Now what is this omega? This omega here is the frequency of the input signal. Now we already know what is that. This omega of the input signal is 2. So if you evaluate this h of omega at 2, that means h of 2 is going to be equals to e to the power minus j 10. Now have a look at this h of 2. We have obtained the same factor as we have obtained by the observation. This is the same as that of this factor, this one guy here. These two are the same. So we have formally proved how we can calculate the value of h of omega. Now this must be true for all kinds of complex exponentials. Let us take one more example. Say we have example. Let's consider the same system but with a different input. So the system is same, that is y of t equals to x of t minus 5, but the input now, let's change the input to say cos 2t. Now let's give this signal as an input to this LTI system. Now by mere inspection, we can see that if we give this signal as an input to this LTI system, the output is going to be y of t equals to, now the signal is being delayed, so that is cos 2 t minus 5. So that is going to be cos 2t minus 10. Now this we have obtained by mere inspection. Let us prove the same using the concept of complex exponentials. Now in order to do that, we must note that the input signal here, that is cos 2t, can be expressed as a linear combination of complex exponentials, and that we can do using the Euler identity that says that this x of t, that is cos of 2t, can be expressed as e to the power j2t plus e to the power minus j2t, and being scaled by half. So I'll simply write that as this being scaled by half, so half e to the power j2t plus half e to the power minus j2t. This is from the Euler identity, and now we can apply the property of the linear combination of complex exponentials. So here we have two complex exponentials, x1 of t and x2 of t, and we know from the property of LTI systems that if we give these complex exponentials as input, we'll get the same combination of linear combination of complex exponentials at the output with a scaling factor of h of omega. So let's find those scaling factors one by one. So for x1 of t, if we give x1 of t as an input, that means if we give half of e to the power j2t as an input, the output is going to be h of omega half e to the power j2t. Now this omega has to be evaluated at 2 because here the input omega is 2. Similarly, for half e to the power minus j2t, it is going to be h of omega half e to the power minus j2t, where this omega is now minus 2. Now we already know what is this h of omega. From the previous example, we have seen that because it's the same system, h of omega here we have evaluated as e to the power minus j omega 5. So let's replace the values of omega in that equation. So we know that h of omega is e to the power minus j omega 5. Therefore h of 2 is going to be equals to e to the power minus j 10, and h of minus 2 is going to be equals to e to the power j plus 10. If I simply replace these values here, y of t, the resultant output, is going to be equals to the sum of the individual complex exponentials. So if we add these complex exponentials, we simply get as y of t equals to h of omega. What is h of omega here? It is e to the power minus j omega 5 times half e to the power j2t plus the other complex exponential, that is e to the power. Now this, we have already evaluated this factor at omega equals to 2, so that is going to be e to the power j 10 times half e to the power j 2t, and the second exponential is going to be e to the power j10 times times half e to the power minus j2t. You can see that this factor is reflected here, and this factor is reflected here. So this is h of 2 and this is h of minus 2, and if we simplify this, we are going to get y of t equals to cos of 2t minus 10. Now this output is the same as that we have obtained from mere inspection. So we have proved it formally using the concept of eigenfunctions, that if we have a linear combination of complex exponentials as an input to an LTI system, we get the same combinations of complex exponentials but with a scaling factor of h of omega, where the omega is the frequency of individual complex exponentials. We shall see more into this in the next module.